So today we're going to be talking about graphing square root functions. We're not going to be doing all of the roots. There are cube roots, there are fourth roots, but the idea and the relationships are going to be very similar. So pay attention with square roots and it'll help you understand the rest of the roots. First, we want to do a comparison, something that we know compared to something that we don't know. So last unit you guys studied quadratics, and you've got the x squared graph and the x squared function. This is just the parent function, if you recall. So we've got our squared, so we can do a table. If you've forgotten, it's really easy to do a table on your calculator. If you just go into y equals, and I can type in x squared. If I do second graph, instead of going to the graph, it goes to the table. And that gives me a nice handy little graph here. So I've got, let's see, we've got 0, and then 1 is 1. And then we've got 4, 9, 1, 4, 9, 16, 25, 36, 49, 64, and 81. So we've got a table of values here for our x squareds. Now, if we do the same thing with our square root function, if I go to y equals, I can type in the square root of x. And then again, I'm not as interested in the graph, but I want to look at the table. So it's interesting because I've definitely got some decimals here. I've got 0 and 1, but then the square root of 2 is 1.41. And the square root of 3 is 1.73. And then 4 is 2. And then 5 is 2.24. And 6 is 2.45. And 7 is, let's scroll down a little bit here and see what we got. 7 is 2.65. 8 is 2.83. And 9 is 3. So when we look at these values, the question here asks us to ignore the points with decimals. So I'm going to cross out all the points that have decimals because they told us to ignore the points with decimals and just look at the ones that don't have decimals. What do we notice about the points? So I have 0, 0. I have 1, 1. I have 4, 2. And I have 9, 3. So if I look in comparison over here, the first couple of them are the same. 0, 0 and 1, 1 look the same. However, I've got 4, 2 over here. Over here I have 2, 4. They're similar. Here I have 9, 3. But here I have 3, 9. So what I notice is that it's the same numbers. Just notice the only thing that changed is their order. Now 0, 0 and 1, 1 are probably switched order as well. It's just that it's the same numbers. So it's kind of hard to tell. But considering that both of these, 2, 4, 3, 9, they switched places, we're going to go with they all did. So what we ended up with was the same numbers. They were just in a different order. So what does that mean? When we look at a situation, what does that mean when we have the same numbers but in a different order? These functions are inverses of each other. By definition, this means that the domain and range and the range switch. If you remember inverse, it's the undoing of a function. So the input becomes the output. The domain and range switch. So that's why the x values and the y values switched places. Now if we plot those points that we had in common. So we had 0, 0, 1, 1, 2, 4, 3, 9 is going to run off my graph here. And if you remember, x squared, that was last unit, quadratic unit, it does that on both sides. It is symmetrical. So this was the graph of x squared, and if you recall, we called that a parabola. That was a parabola. If we're doing the square root of x and we're plotting those points, we had 0, 0. Let's see, it was 1, 1. It was 4, 2. And then it was 9, 9, 3. So that gives us this one as well. We also have to remember that when we do those square roots, that when I take the square root, technically there are two outputs, so it's positive and negative. You know, so we could do the positive and negative of both of these. So that would put me with the -1 and the -2 and the -3. So we would get something that would look like this. And that makes sense. If they are inverses and their x and their y's literally switch places, if you remember from that very first unit when we did transformations, when we did reflection over the line y equals x, that was the rule. The rule for reflecting those geometric shapes over that line y equals x was that the x and the y switched places. So that means that inverses, since inverses, the x and the y switch places, they are just a reflection over the line y equals x. And that is true for all inverse functions. So that means that's true for x cubed versus the cube root of x. And that's true for x to the fourth and the fourth root of x. That's true for any other inverse functions. You learned exponentials last year in Math 1. Their inverse is going to be a reflection over y equals x. All functions, their inverse is going to be a reflection over y equals x. And so this is going to help us find out what is the graph for the square root function. Now, as a result, the graphs have the same number of points, but the x and the y coordinates have switched places. So x and y have switched places. This causes the graph to have the same shape. So it's the same shape, but to be reflected over the line y equals x. And that just sums up kind of what we said up above. Now, as far as talking about the square root function, when we take this graph and we reflect it over that line, if you recall, it made a graph that looked something like this. And if we're talking about a function, what kind of problems might there be with a graph that looks like this? If you recall, to be a function, you had to have every x value can only have one y value. And if we're looking at graphs, we had something called the vertical line test that could help us figure that out. Well, this is going to fail the vertical line test. This is not a function. However, we want to have a square root function. So if I want the square root function to be a function, it cannot look like this. The problem comes from, if I take the square root of 4, it's plus or minus 2. You talked about this when you were using the quadratic formula, or when you were solving quadratics last unit. Anytime you took a square root, you had to do the plus or minus. There are two outcomes, and that is the definition of not a function. I have one input with two outputs. That is not a function. So in order for me to have a square root function, there can only be one output. And so when we have the square root of x squared, so some perfect square like 4 or 16 or 25, if I want it to be a function, I need to designate that I'm only going to get one output. And the way we do that is we say that it's going to be the absolute value. Or if you remember, absolute value just means the positive. It's going to become positive. So we're going to designate that the square root function is only the positive output. So we're just going to kind of ignore the negative one. And if we ignore the negative one, it gets rid of this half of the graph. And if we get rid of that half of the graph, then all of a sudden, we are passing the vertical line test. And it is a function. It passes the vertical line test. So we have to define the square root as the absolute value, or the positive output. We're only going to use the top side of the graph. So that gives us this as our parent graph. Important things that we want to point out. Just like a parabola, it does still have a vertex. And just like the parabola, its parent graph vertex does start at 0, 0. All right, so it starts here at 0, 0. Now, because we have taken this second half of the graph off, notice its end behavior. It's very unlike a lot of our other graphs. We're used to graphs having, arrows on both ends, and this one doesn't. It actually comes to a dead stop. So its left end behavior, okay, it's not going to infinity. Its left behavior is that it's going to 0, and it stops. So its left behavior is that it's approaching 0. Now its right end behavior, on the right side of the graph, this arrow is going up ever so slightly, but it's going to continue to go up ever so slightly, and it is going to be going to positive infinity. As it goes up and up and up and up and up and up, it is continuing on, but it does come to a dead stop here. And we talked about that is because we're not using that negative half to keep going. It's domain. Domain is our x values. So remember, we're using our interval notation, and we go from left to right. We always read left to right. So on the left-hand side, it is actually starting at 0. And it is equal to 0. I can take the square root of 0. So I am going to include that. And then as I go to the right, I am following my arrow ever so up, 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 up. And then it's also going as far right as it possibly can. And so it is going from left to right from 0 to infinity. And don't forget, you can't be equal to infinity, so we use that lovely little parenthesis. Now range is up and down. So domain is left to right, range is up and down. So range is also starting at 0 and is equal to 0. And then it is going up, 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 ever more. And so that would be positive infinity as well. Other things to think about, like why does it stop at 0 for domain? Even if we did have the other half on here, if we had kept it on the other side, that wouldn't have changed the domain. The domain would have still started at 0. So why does the domain start at 0? So let's think about our function for a second. We're dealing with the square root of x. What's the square root of negative 5? If you remember your quadratics unit last unit, we did imaginary numbers. That's an imaginary number, but imaginary numbers don't show up on the graph. So all of these square roots of these negative numbers don't show up on the graph because they're imaginary. We don't take the square root of a negative number and get a real number. They're not going to show up on the graph. So that's why our domain is restricted as well as our range. We know why the range is restricted. We did that ourselves. We restricted the range to just be the positive outputs. That was the definition of the square root function. We had to redefine that. So we set the range. We are the reason that the range is just this upper half, but the domain was already set. The square roots of the negatives are not real numbers, so they don't show up on the graph. Do notice the lack of symmetry. We cut it off. Again, it had symmetry when it was the square. It had this other side of a parabola, but we erased it. We got rid of that symmetry. And so now it doesn't have any symmetry. We cut the symmetry off. It does follow a pattern, just like our quadratic followed a pattern. We have 0, 0. We're taking square roots. So it's always, if you remember for squares, if we went over 1, we went up the square. If we went over 2, we went up 2 squared. Well, x and y have switched places. So now instead of going over and then up the square, I'm going to go up and then over the square. So wherever my vertex is, if I go up 1, I'll go over 1 squared. If I go up 2, I'll go over 2 squared. If I go up 3, I'll go over 3 squared. So it's the same pattern as x squared, except switched. X and y have switched places. And so our pattern also has to switch places. Now, all graphs transform using our transformations that we learned in Unit 1. So let's review real quick to make sure that we remember how all of these things transform. So remember, to translate, that's up, down, and left, right. So to go left and right is always inside the function. And if I want to go left, I add. If I want to go right, I subtract. So that would be something like square root of x plus 2, or square root of x minus 2. If it is outside, that is what moves it up and down. Up is positive, down is negative. So this would be something like square root of x, but then outside of it is a plus 2, or a square root of x, and then outside of the radical is a minus 2. That would be transforming up, down, left, right. Reflections. Now, reflections get interesting because it doesn't have symmetry. So reflecting the parabola left to right didn't really change anything, because if we reflected it left to right, it still was a U-shape because it was the same on both sides. But we could reflect the parabola up and down, and that would change it. But reflecting this square root, because it just goes off to one side, I can flip it left to right, and I can flip it up and down. So we need to remember our reflections. So if you remember, if we want to flip it horizontally, if I want to flip it left to right, that's going to be inside. So if it is multiplied by a negative, that would flip it the other direction. So something like square root of x is still going to go to the right, but the square root of negative x is going to go to the left because it's going to get flipped. If we want to flip it up and down, that's always outside, and that's true for all transformations. So if I've got just the positive, square root of x, it is still going up the way it's supposed to. But if I put that negative outside of the square root, that's just going to flip it down. So I can go right or I can go left, depending on if there's a negative inside. And I can go up or I can go down, depending on whether there's a negative outside. Dilations. All right, we do have dilations. So far, we're just doing vertical stretches and compress. Vertical stretch and vertical compress. Don't forget that when we multiply by a number larger than 1, so if we have some coefficient in front of the radical that is larger than 1, then that is stretching it. If it is less than 1, then that's going to compress it. And all that is changing is your up value. All right, so these are all of our transformations. We just want to review those real quick before we start actually graphing. So when I look at this particular square root, I realize that it has been shifted to the right 3 spaces. So instead of starting at 0, 0, it's going to go right 1, 2, 3. So here's its vertex. All right, so we got a vertex of 3, 0. So our vertex shifted. So we went to the right 3 spaces. Now the shape didn't change. So it's still up 1 over 1 squared. Go back to the vertex. Up 2 over 2 squared. That's 4. Up 3 over 3 squared. It kind of runs off of my graph over here. So that's going to give me a square root function. I don't do the other half because the square root doesn't have the other half. This one is getting shifted up 4 spaces. So instead of being at 0, 0, it's going to start up here at 0, 4. My shape is still the same. So up 1 over 1 squared, up 2 over 2 squared, up 3 over 3 squared. And that gives me my half parabola. You do want to try and make it as, roundy, parabola-y as possible. It is not a straight line. It is definitely a curve. So you want to try and make it as curved as you possibly can. There we go. And that gives us our square root. As we go down here, we've got more to practice. We've got these negatives to look for. So notice, no addition, no subtraction. I'm starting at 0, 0. The negative is outside, so that's going to flip it down. So instead of going up 1, I'm going to go down 1 over 1 squared. Back to the vertex. Down 2 over 4 squared. Down 3 over 3 squared. So it is the same shape, but going down instead of up. For the next one, again, no translation. It didn't get slid up, down, left, or right, so it's still starting at 0, 0. But this negative is inside, which means that that's going to flip it to go that way. It's still going up, but it's going to go left instead of right. So I'm still going to go up 1, but I'm going to go left 1 squared. Still going to go up 2, but I'm going to go left 2 squared. Still going to go up 3, but I'm going to go left 3 squared. So that's going to make my graph. Notice that this is a very repetitive pattern. I'm doing the same things over and over and over again. I just have to know which way it got slid, which way it got flipped. But the pattern for the shape is the same no matter where it lands on the graph. For the next one, I do have a translation. It got slid left 3 spaces. So it's not going to start at 0, 0. I'm going to go left 3 spaces. So here's my vertex. No negatives, so it's still going up and it's still going to the right. It's still going this direction. However, I am stretching it. I'm going to be stretching it. Multiplying by this 2 is bigger than 1, so that's going to stretch it. That means for my vertex, instead of going up 1 and over 1 squared, 1 times 2 is 2, so I'm going to go up 2 and over 1 squared. So normally it's 1, 1 squared, 2, 2 squared, 3, 3 squared. But when I do a vertical stretch, I'm multiplying these numbers times 2. So I'm going to go 2, 1. I'm going to go 4, 4. I'm going to go 6, 9. So I went up 2 over 1 squared, up 4 over 1, 2, 3, 4. So notice my over distances. It's still 1, 4, 9. These didn't change, but my up numbers did. So I'm going to go up 2, 4, 6 and go over 9. So my over number, it stretched it vertically. It stretched it out, made it a little taller. It's not as squishy up there. When the number is less than 1, that just means that it's getting compressed. So here we didn't shift left or right any, but this number is less than 1, so we are going to compress this one. This one's going to actually get, you know, swished down a little bit. Normally we go 1 and 1 squared, 2 and 2 squared, 3 and 3 squared. But we're going to multiply all of these times 1/2. So this one is going to be 1/2. This one's just going to be 1. This one's going to be 3/2. And for graphing purposes, you know, that's 1.5. So we didn't get shifted any. We're going to start at 0, 0, but I'm going to go up 1/2 and over 1. Then I'm going to go up 1 and go over 4. Then I'm going to go up 1.5 and over 9. So my over numbers, these stayed the same, but it definitely got squished down to the bottom. The last little trick that you might run into is occasionally they've multiplied it by something on the inside, and this poses a problem. We're only doing vertical stretches and compresses. But what we can do is kind of trick it into getting in the graphing form that we need it to be. What that usually means that we're going to have to do is we're going to have to factor out whatever this number that's getting multiplied by x is. So in this case, it's 4. So if I pull out that 4, it's going to give me x minus 3. I do have to factor it out of both of them. Sometimes you might end up with a fraction over here. Even if it's not something like a common factor, you still have to pull it out. And then what we have to do then is separate our square roots. So now I have the square root of 4 and the square root of x minus 3. The square root of 4 I know. That's 2. Sometimes it might even turn out to be some kind of decimal number for graphing purposes. If you get something like 5 there, then you're like, oh, it's 2 point something. And we can rough estimate. But that means that when I graph this, I'm going to treat it like this, because this I can look at and say, oh, it's shifting right 3 places, not 12 places. And it's getting a vertical stretch of 2. All right, so we're going to stretch it out and get taller. If I had looked at this and tried to go right 12 places, that would give me a very different graph. So it's important that you do this before you graph it. For this one, if we pull out the 9, that'll be 9 and then x plus 4. Notice it doesn't mess with this minus 5 at all. It still just stays minus 5. When I separate it, I get square root of 9 and square root of x plus 4. I still have the minus 5. The square root of 9 is 3. So then I still have the x plus 4. And I still have the minus 5. So now when I think about it, it's going to be going left 4 spaces. It's going to be going down 5 spaces. And it's going to get stretched by 3. And that's how we figured those out.